Hello, and welcome to Getting Started with Julia and Machine Learning. My name is Anthony Blaom. I am a Senior Research Fellow at the University of Auckland, and I'm joined today by Samuel Ocon, who works for the Applied Machine Learning Research Group at the Technical University of Kaiserslautern, and also the German Research Center for the Artificial Intelligence. So before we go much further, let me explain how we are going to communicate. So we will be taking our questions from using a forum called Pigeonhole. And you can see there on the screen a link. Also, there's a banner, I hope, that has appeared to show you where to go. And let me just show you a little bit what that looks like. So I'm going to move my particular Pigeonhole picture here. So you'll have something like this. Questions, you're going to enter questions in the space here, and they'll appear here on the screen, and you can up and down vote them. And Samuel and I will be both answering questions verbally, depending on who's speaking, and then the other will also be making written answers to questions. And these will appear in the comments. So you may have to click on the comments to see answers, I guess. I'm new to this forum myself, so have a little patience. All right, so that's what that's about. That's how we'll be interacting. Now, you can feel free to use the StreamYard chat, I guess, if you would like to communicate with other participants. But we won't be monitoring that forum. We'll just be monitoring the questions that you post at Pigeonhole. So I'm now going to outline a little bit how the workshop's going to work. So we'll start off by, I'm going to introduce you to the workshop resources and get you going with a little installation that's going to help the second part of the workshop run a little smoother. After that, I'll give a kind of a mini, while that's going, I'll give a kind of a mini lecture on supervised learning, which is the kind of learning that we're going to focus here in this workshop. And then there'll be a longer section after that, introducing just Julia basics. So it'll be a live coding session where you can keep up with what we're doing, and we'll go through Julia basics. So it'll be kind of the core part of the workshop. After that, I'm going to, or towards the end of that, I'm going to introduce you to a second way of interacting with Julia. We're going to start interacting just at the command line, and towards the end of that, we'll be interacting via what's called a Pluto notebook. And there'll be a shorter section on things called data frames using these notebooks. Data frames are containers for manipulating tabular data in memory, a sort of a basic staple for data science. And then after that, I'll be handing over to Samuel, who will help you build a machine learning model using a toolbox called MLJ, which we are developers of. So that's how the workshop is going to run. Now, I don't see any questions yet. I'm hoping that people hear me. There's a question. That must mean I'm getting through to somebody on the planet. Okay, so where can I find the workshop resources? And the LinkedIn page. Okay, so I think that's a question that is already answered. Or maybe that's a comment. Okay, so I'll carry on for now. And take yourself, so now just go ahead and find yourself at the JuliaCon website. I'm going to take you to the resources for the workshop now. So once you're there, go ahead and click on the schedule. And hopefully you'll get today's schedule, which for me is Wednesday, but for you probably will say Thursday, because most of you are probably in a different part of the planet. And click on our workshop, which is the second one there. Now, if you go all the way to the bottom of that page, you'll see a title, Resources, and something that says Hello Julia. you just go ahead and click there. And that will take you to a GitHub repository, which collects together the resources, extended resources for this workshop. So this includes things that we're going to go through during the workshop, but also other helpful material. I'll just point out a few key things for now. There'll be slides from the talk. Actually, eventually there'll be extended version of the slides I give you the talk. And there are a few useful cheat sheets here, one for Julia itself, one for Dataframes, and one for the machine learning toolbox MLJ that we're going to talk about. You will also be able to, by clicking on this link here, see all a number of demonstrations that we won't get time to present in the workshop, but you may find useful, and notebooks in various forms, also reproducing what we will be doing in the workshop. But more about that later. Okay, so if I just go back to here, the next step that we need to do together here is to install some extra resources that will help some of the workshop later on go a little quicker. So click on here at the very top of the Hello Julia repo, and that will take you to this page here. So if I just to show you again, if you go to the top of the resources page and you click here, then you come to this important page here. Now, we're assuming that everyone here has already installed Julia on their computer, version 1.7. And now I'm going to give you some instructions, which is basically what this is going to do for you is install a customized version of the notebooks that we're going to use, these Pluto notebooks. You don't need to understand these instructions. You just need to follow them, and hopefully it'll all go smoothly. So go ahead and copy this first block of code here by clicking on the copy paste icon in the corner. And now what you need to do is boot up a Julia session. And I'm assuming that you already know how to do that. For me, that means I launch my Julia sessions from the REPL, from a shell, a Unix shell, or terminal. You might know this as a console if you're working from Windows. And I just type Julia, and that will boot up a Julia session. Some of you may need to click on an icon on your desktop somewhere to open up this sort of a view that you see now. So at the end of the day, what you're aiming to get is a little prompt here that says Julia. And once you get to that prompt, you're going to paste that code that we just copied before. That should start some kind of a process happening. It's it won't look exactly what you see here, but it'll look something like what you see here. And so long as you're not seeing red, everything's going fine. Now, if this doesn't work for you, that's not the end of the day. You'll still be able to follow along with most of the workshop and participate. But I expect it'll work for most people. Now, go ahead and make sure you hit return a couple of extra times to make sure you execute that very last line, which is set up. Okay, so while that's going, I'm now going to, working in the background, this is going to take about a few minutes, like 7 minutes or so. I'm going to start the kind of mini lecture on machine learning. I'm just going to check my other questions here. I don't see any pressing questions here. I think I've answered the question where to find the workshop resources. And now I'm going to add that link just to be on the banner there as well. Let me go ahead and do that so that people can find the resources if they come late. All right, so now we're going to talk for just 10 minutes or so about machine learning. I'm going to start with a clarification. So you'll hear people talk about machine learning, and particularly I see in the Julia community, and they'll often mean, when they use that word, they'll mean something that I would call deep learning or neural networks. And for me, these are different things. So For me, deep learning and neural networks are a special class of algorithms in machine learning. And when I use the word machine learning, I'm actually talking about something more general. So a more general class of algorithms for doing machine learning. Here's a picture. You don't need to fully grasp, but just to give you an idea of the variety of machine learning models. So every kind of little white box here is some kind of machine learning model, some kind of algorithm for learning. And you know, there's quite a diversity, and also many different ways to kind of try and organize machine learning algorithms. It's not actually a simple exercise. And we see here that these sort of neural network type models account for just a small part of that. Now, neural networks, deep learning methods, have been very successful in the area of image processing and video and that kind of thing. But chances are, if you're moving to other applications, you'll want to know about some other kinds of models, not just neural networks, because chances are other models may perform better, and very often they're actually easier to train than neural networks. So with that clarification out of the way, let's talk about supervised learning. So supervised learning is about trying to predict some particular variable, which we call the target variable, given that we know some other variables in the problem which we'll collectively refer to as x. Now, we're not learning to do this in a vacuum. The idea is that we actually know both the variables, both the target variable and the other variables. Historically, we have some data about those things, and we want to take that data and then use it to make predictions of the target when we don't know what it is anymore, but just the other variables. So let's leave the abstract and give you some examples. So you may be a meteorologist, for example, and you've measured the temperature and pressure at various places on the planet. So that gives us a bunch of these so-called input features x, longitude, latitude, temperature, and pressure. And then you've also, I suppose, measured the wind speed. But then the idea is you want to go to some new place on the Earth where you've measured the temperature and pressure, or the average temperature and pressure, or whatever, and you would like to give a kind of prediction of what the wind speed is. So there you have some features, and the target is the wind speed in that case. Another example might be you are doing genetics, or you're a biologist or someone like that, and the input features here are DNA sequences. So you're looking at genes, you're looking at genetic sequences, and the thing you're trying to predict is whether a person is likely to get a certain disease based on their genes. You might be classifying emails, junk or not junk, so that's another example. You might be trying to classify handwritten digits as 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And then one last example that we are going to get involved in ourselves towards the end of this workshop is the Titanic disaster. And in that case, the inputs there are properties of the passenger. So for example, their sex, what class they traveled, what fare they paid, where they got on, and a couple of other features. And the question we're trying to answer is whether they survived the disaster or not. So there are a few examples of machine learning, of supervised learning applications. Now, for the purpose of discussing the machine learning basic principles, I'm going to turn to yet another example where I imagine that you have thermometers spread around the house. So in each room of your house has a thermometer, and you are measuring the temperature, say, on the hour in each of those rooms. And you've recorded that information, so you've got some historical times and rooms, and you've also got this temperature, which is going to be our y, our target variable. So the idea now is at some different time in some room, you want to know what you want a prediction of the temperature. Maybe it's not on the hour, maybe it's on the half hour or something. Now, we're going to make this even simpler and just forget about the room for a moment. Just pretend we will just say in one room. Then we can visualize the data. Our inputs here are being written on the bottom, and the vertical axis here is the temperature. And we just have a bunch of dots, a bunch of points in the plane. So then remember that what the problem is, what the objective is here is to make predictions for new inputs. And the way we do that is one way we could do that is to fit some kind of curve to the data. So we might try to fit a straight line, or maybe a cubic, or maybe something, a polynomial of some higher order. And we're not so concerned here about the algorithm which picks out a particular curve. For the purpose of this workshop, we just regard that as a black box. But we are concerned about how one goes about deciding which of these models is actually going to be the one we should use in practice. So we already have a little bit of suspicion about this purple curve or pink curve here, because although it goes through every single data point here nicely, it's got a lot of wobbles in it, and that seems to be a bit strange. So how we go about assessing the various models? Well, to do that objectively, what we really need is more data. So now I'm going to correct myself and say, well, actually, I wasn't measuring the temperature every hour. I was actually measuring it more often. I have half-hourly data as well. And that's what we're going to look at in deciding which model we ought to use. So here's now all the data that I had, not just the data I used to train the model, but some extra data which I held back. Let's throw away the training data and just look at the held back data, or test data as we call it. So now we're in a position to more objectively decide which of these various models are the ones that are likely to perform the best on new data. To make this a proper quantitative thing, we have to make a decision about exactly how we define the error. And we could, in this example, we could do something like measure the sum of the square deviations from the curve and our points. So that would be one way to quantify the measure. Once we have that agreed upon measure, or metric as we call it, we can then pick the curve which minimizes the error, and away we go. So that essentially is the machine learning, supervised machine learning workflow in a nutshell, the most basic form of it. And sort of from a philosophical point of view, all supervised learning really is just curve fitting. I mean, you can kind of think of it that way, if you like. Now, I'll just summarize a little bit. So what's the setup here? The setup is always the same. You have some historical data, which you've divided into things you call features and things you call the target variable. And the basic workflow is you split the historical data into separate training and test sets. The test set you kind of put in a cupboard, lock, throw away the key, and don't touch when you're training. Then in the second step, you train the model using the training set. You get model predictions. Now open up the cupboard and grab your test set and get predictions for the test features. Call that y hat, for example. Then you compare that y hat with the actual historical test values of the target variable. Quantify that using some agreed upon measure, metric. And you repeat the process for different models or different values of a particular model's hyperparameter. So a hyperparameter is something like the degree of the polynomial that we looked at in that example before. So that's the basic machine learning workflow. I'm going to go have a look here and see if there are any questions coming up about that. Okay, I think I'm going to mark this as answered, or it's answered already. Oh, good. Okay, so we seem to be on track here. So now that's the little mini lecture. Next thing we're going to do is we're going to, I'm going to say one more thing about this. So if we go back to our examples, we see the targets actually come in two different kind of flavors. There's the continuous sort of variable, which we had in the temperature example. Another example would be this real estate one, which I didn't mention, where we're trying to predict the selling price of a house. And so there you can kind of literally think of supervised learning as fitting a curve or a hypersurface in higher dimensions. But then we have this other kind of variable like is junk or is not junk, or survived or is not, did not survive. These are discrete, these are examples of discrete target variables. And there we can't really think of this as a curve anymore, not literally. And this example that we're going to talk about later, this Titanic example, is of that kind. So in this case, the thing we're trying to predict is discrete. So we call that kind of a problem a classification problem. And let me just give you an example of a classification model that's quite easy to understand, which is called a decision tree. And this is actually what you're going to be training towards the end of the workshop. I see a question here. I'm just going to pause for a minute. Why are they called hyperparameters and not parameters? Is this an important distinction? That's quite a good question. So let me answer that now. So the hyperparameters in your problem, they're things that you as the user kind of fixes ahead of time. And what we normally call the parameters of the problem are things that get learned, that you as the user don't actually control directly. So you're going to run, for example, in the example of the fitting the temperature problem, when you're trying to learn the temperature, the hyperparameter is, say, the degree of the polynomial. So you say, I'm going to look for a third degree polynomial. Then you run your algorithm and it fits a nice third degree polynomial to your data. And what it's learning there is some coefficients, right? The coefficients of your constant, your coefficients of x, your coefficients of x squared, and your coefficient of x cubed. So those things are what we tend to call the parameters of the problem. And they're the things that get learned. And the hyperparameters, these are the things that you fix ahead of time. Now, it can happen that this distinction between parameters and hyperparameters gets blurred when you start to automate the question or the step in your process of deciding what hyperparameters to use. But in the first step, they're fixed. And then later on, as you try to optimize and find the best parameter, you may actually automate that process. And in that sense, these hyperparameters become learned parameters. So this isn't a black and white distinction necessarily. Let's see, we'll say that one is answered. I guess I am on the right thing. It looks like it's not appearing anymore. Okay. All right, so now let me talk about this decision tree. So this is, remember the thing about the Titanic disaster. So you've got a bunch of passengers and things you know about them, and you want to know whether they survived the accident or not. So I'm not going to say how a decision tree, how you find this decision tree, but I'm going to give you an example of a decision tree that has been fit to the data, which is represented by this picture. And all a decision tree really is a bunch of questions that you're going to ask. It's when we call it a tree, but really it's an inverted tree. And we start at the top. And the first question in this case is, what gender is the person? Okay, let's suppose it was male. And so then the next question is, what age is the individual? If we suppose that the age was less than 9.5, then the tree is telling us, okay, we have a conclusion now. That individual died in the accident with a probability, a survival probability of 17%, which means that they likely died. So that's what an example of a decision tree, a very simple kind of idea. It's not the most best performing model most of the time, but it's actually the basis of a lot more of other more sophisticated models. So it's a very nice one to learn about. Okay, so that's all I'm going to do with the sort of chit chat on the theory here. It's time now to do some actual machine learning. And as I said before, I mean, not machine learning, some coding. Get to the machine learning later. So now we're going to go a step back now and just think about coding and think about basic Julia. Let me have a look at the questions here. Okay, so what I want you to do now is to open up. So there'll have been this process that you got started before somewhere. It looks like for me it has already ended because I've got back to my Julia prompt here. You'll see a bunch of LD warnings. You can just ignore those. And if your process is still going because your computer runs a little slow or you had more somehow to install, that doesn't matter because we're not going to use this yet. So in any case, what you might like to do now is open a second Julia process. So for me, that might mean opening a new shell or console and typing Julia again, or it may mean clicking on an icon again, so that you have a second Julia process, and that's the one we're going to work with here. So once you've got this Julia prompt, you can. I invite you now to kind of follow along as best you can with what I present now. So the first thing to understand about Julia is it works just like of course, like a calculator. So I can enter in some sum like 5 + 6, and it gives me I hit return and it gives me the answer. The next thing that you want to know about the REPL, it's the most useful thing to know about the REPL is that you can use the up and down keys on your keyboard to navigate the history. So I can go up, use the up arrow, and I'll reproduce the 5.6. If I press the down arrow, then I'll go back to a blank line. So up arrow, I go back to 5 + 6. Now I can edit this line, and I can do something like, let's take the square root of 5 + 6, or maybe let's do 5 + 4, so I know what the answer is actually going to be. Should be 3, right? And it is, so 3. So we can do all the kind of standard scientific functions are provided, built in. So I can do things like compute the sign of a number. In Julia, pi is pi, so that's the sign of a number. And another very important thing is how we get help about a particular function like this. And the way we do that is using the question mark. So you're at the Julia prompt, then you type in a question mark, and that changes the prompt to yellow, and it now says help. If I hit delete, then that will disappear, but let's hit the question mark again. And now I can type in, say, for example, sine, and I'll get a description of the sine function and how it works and what it is. Okay. The thing we're going to talk about is something that's pretty important if you're doing any kind of maths or stats, and that is arrays. And in particular, we'll talk about vectors and matrices. Give me a sec here. Lost one of my screens. Right. So how do you define a simple vector in Julia? Well, you use square brackets and you do something like this. So here's a vector 1, 2, 3. Vectors have a length. That's something that's useful to know. And the way we access a vector is we use square brackets as well. I mean, like, say, for example, if I want the second value of that vector, I go v square brackets 2. So pretty straightforward. If I want to, the vectors are also mutable, which means I can change individual elements. So if I wanted to, let's use the up arrow here to save some typing, I can actually change the second element. So maybe I want to make that 42. And now if I type v, then you can see I've changed the second element of the vector. So vectors are mutable, we say. You can also change their lengths. We'll see an example of that in a minute. What about matrices? Or, well, what about, how should I think of this? I should think of this really as a column vector, the way it's displayed here, even though I enter it as a kind of a row. You should think of this as a column vector. How then how would I actually define a row? Well, in that case, you leave out the commas. So maybe 4, 5, 6 with spaces in between. That gives you actually a 1×3 matrix, which then sort of is suggestive of how we would define a matrix now. It's just a number of rows, so 1, 2, 3. And you separate the rows either by entering a return key like this, or by using a semicolon. That will also work. 7, 8, 9. So that's how we get a matrix. We can access the elements of a matrix much like we would a vector, but now we need, say, 2 arguments, first for the row and second for the column. That's not going to work because we don't have a 4th column, but that will work. So there's the element in the 2nd row, 3rd column, and you can mutate elements just like you mutate them for vectors. You have you also have a length for a matrix, which is the length if you would just join all the columns together, which is how the matrix is actually stored internally. So that's kind of a linear index, indexing kind of idea. But then if you want to know the actual dimensions of the matrix, we use a command called size. Now, size is returning something a little bit different. This 3, 3 here has round brackets instead of square brackets, and that's what we call a tuple. That's a little different. We'll talk about tuples in a minute. Now, Julia has sort of basic linear algebra provided built in. Maybe it doesn't. Maybe for this I need, what do I have? I happen to pick a singular matrix. Okay, so let me change that. Let's change my matrix to be, and we'll see this later, a random matrix, and maybe I'll have better luck. And let's try inverting that matrix. Okay, that one was not singular. So there's some basic linear algebra provided built in, but if you want to do something more fancy like singular value decomposition or something, then you would import one of the standard libraries that Julia provides. So that's part of the Julia installation. You don't have to download it from somewhere, but you need to actually call it. And the way we would do that is we would go using, in this case, linear algebra. And that would then allow us to use some more advanced functions. So there you go, singular value decomposition of this matrix. Okay, we're not going to need to that anywhere here. You can relax. Okay, so the next very important thing to do, but let me just have a look. For some reason, don't seem to be seeing many questions on that page, on my admin page. So I'm going to have to keep monitoring here. Is there logic in splitting a given data? Okay, let me have a look at some of these questions. Seems like they're being answered. Here's one that's not answered. Is there an argument to the square root function to return 3 and not 3.0? Aha, well, that's a subtle question. The really important question comes after. What if I want to test whether 3 is equal to 3.0? So the question was, maybe I'm not going to answer the question completely, but if I take the square root of 9, let's have a look at that, and we saw that it was 3.0, you might be thinking about, well, why doesn't it return an integer if it can? This particular function will return, won't return an integer, it returns a float, as you see here. But what you can safely do here is do this kind of testing. So compare 3, the integer, to 3, the float, and you'll see that it's still true. So while you might be surprised that the square root of 9 is not an integer, it's still something that is equal to the corresponding integer. So I'm not completely answering the question there, but perhaps clarifying why it doesn't really matter in some sense. So we'll call that answered. Okay, I'll now continue. Now, the next thing I want to talk about is variables. So variables in Julia may not work the way you're used to if you're coming from, say, R or maybe a low-level language like C. They are what you would be used to if you're coming from Python. So variables in Julia really just kind of pointers to objects which exist in their own right, and they're very ephemeral in some sense. So let me explain that really with an example. Let's suppose we have a vector 1, 2, 3, or 1, 3, 5. I don't know. Here's a vector. What that bit of code actually says is it says, first of all, it says create somewhere in memory a vector, an object, which we call a vector, which has these elements, which exists in its own right. So this object exists somewhere on the computer on its own right. So that's step one, create this thing. And step two is saying, well, the symbol U is understood now to point to this particular object. Okay, it's pointing to this object. It's not literally this object. It's a symbol which is redirecting us to this object whenever we call it. Now, if I go ahead and say U, let's say W equals to U, then that command, that expression there, is telling us now, okay, I now want the symbol W to point to whatever U points to. So sure enough, if I type W at the prompt there, I'm getting 135, but I'm not just getting 135. I'm actually literally accessing the precise new part of memory. So this W equals U here, it didn't copy the 135. There's no new part of memory that now contains a copy of 135. It is literally the same thing. So if I now go ahead and say change, say let's make it the middle element, and I say let's that be equal to 42. So now I've actually changed that one of the locations in memory now with this command. But now because W points to the same thing, then if I have asked the question, what is W, I see that has also changed. So that might be a little bit of a surprise to you if you're coming from, say, R or some other language. So just be aware of that. Variables work a little bit differently. Kind of a corollary of this is that functions in Julia all kind of work pass by reference, if that makes some sort of sense to you. If it doesn't, it doesn't matter. All right, let's check my questions. Okay. So it looks like Sam was doing a good job here of answering my questions for me. All right. So let me carry on. And the next thing I'm going to talk about is tuples, which we saw before when we looked at the size of an array. So in a tuple, let's define one ourselves. A tuple looks something like this. And it's very commonly used when we're dealing with objects which have different types. So maybe I'm mixing an integer here with, say, a float and maybe what we'll talk about strings in a minute, 3 different kinds of objects. And I use round brackets. And this is sort of like a vector because, I mean, it's just a string of different objects, but it's different in a couple of respects. The first way it's different is that I can't mutate the elements of a tuple. I can access them the same way, so I could do that, T1 of 3, but if I try and change cat to dog, I'm going to get a complaint. So these are immutable. They can't be changed, the elements. You also can't make them longer or shorter. So that has certain advantages, which I'm not really going to go into, but basically performance might be an issue whether you decide to use a tuple or a vector. Just as a rule of thumb, if you're needing to mutate, of course you're going to use a vector. But also typically when the data is always the same type, then using vectors, not necessarily, but often when you're having mixed type, you may want to think about using a tuple. Then tuples come in a named version. So let's use the up arrow key and get back to this earlier definition. Oh, it doesn't want to do it the way I had. Okay. Okay, now it's working. So go back and edit this thing here. Tuples come in a named version, which means we can give the various components of our tuple names. Suppose we can call this X, Y, and Z. And this gives us then the option of accessing elements by name. That's kind of the main point. So I go T1.x, and that gives me the X, the thing we named as X. Then we have, let's introduce a few more basic types in Julia. We have strings, and there's sort of 3 basic string-like things that we will encounter in this workshop. The first was an ordinary string, which we sort of already saw before, enclosed in double quotes. The string behaves a little bit like a vector, so I can access, say, the 3rd character of my string. And what is returned here is the second kind of object that is string-like, which is we call a character. So now I'll define a character myself. A character equals, and I use now single quotes, so maybe C. Okay, and I maybe so that's a single character is considered a different kind of object, and the elements of a string are these characters. Then there's a third kind of string-like thing, which is called a symbol in Julia, and that'll be something you haven't seen in, say, a language like Python or MATLAB. I'm not going to say too much about them, but I'm going to tell you how to define one. So here is a symbol, and it's sort of quite, here's the symbol cat, and this is what is called in the business an intern string. I didn't actually know what that really meant. I had to look that up myself not long ago, and I'm not going to try and explain it. It's something to do with the way that the thing is stored in memory. I won't say much about it in this workshop, but basically the reason they exist is to do with Julia's possibility for language reflection. So in Julia, Julia can take bits of Julia code, bits of the language, and actually manipulate it. So that's a very powerful idea. It's called metaprogramming, and associated with that are things called macros. We're not going to talk about them here, but these symbols are kind of make the most atomic objects in that whole business of expressions, code expressions that you manipulate. The basic atoms in that are called symbols, and you'll see them come up, but just think of them as a different kind of string. Another kind of basic object that you might want to learn about is a dictionary, but I'm just going to pass over that for now and talk about functions, which are going to be more important. Let's see the questions. How are we doing here? A question is, here's an interesting question. Are tuples the same as dictionaries in Python? So tuples and dictionaries, I haven't told you what a dictionary is, but we have dictionaries. They are very similar, except in Julia, dictionaries are mutable, so whereas tuples are not. And dictionaries have no associated order with the keys, whereas a tuple has a fixed order. So there's two differences between tuples and dictionaries. But since I'm not talking about dictionaries, I won't elaborate a lot further. So there's a question about whether tuples of L type any. Well, a tuple will perform the say an S vector type L type any. I think that's going to I won't answer that here because it's a bit technical question. Okay, I think we'll carry on. Okay, so we're going to talk about functions now. How are we doing with time? Okay, we need to keep an eye on. Okay, so there's a couple of ways of defining functions in Julia, and functions are important because it saves us having to write out the same thing over and over again. So the simplest way to define a function is just how you would do it if you were in a math class. And this caret symbol here means to the power of. So this is the squaring function. So you just, for example, we can square the number 3 and we get 9. So that's the first way you can define a function. Another thing you can do, which turns out to be very useful, is to define a function without giving it a name. So this function, we had to give it a name. We called it foo. But you can define functions without giving them names. So the way you do that is you go x maps to with this minus greater than. So regard these two things as kind of one symbol here. X squared. Now that doesn't have a name, so Julia gives it a name and calls it generic function number 1. We can't, as users, we don't really have a way of accessing that, but we can apply it to things. So for example, I could take the number. Well, let me show you something first. Here's some syntax which is sometimes useful. Suppose I take that foo function and I want to apply it after the fact, so to speak. So I've got an input 3, and now I want to apply foo after the fact. Then I use this symbol here, vertical bar and a greater than symbol. It's called the pipe symbol, and then that will give me 9. but I can also do the same thing, but with the anonymous function. I never gave a name to, right? That does the thing, and I can chain these things together. So here is square twice, essentially. There's a bit of that's a bit about anonymous functions. Anonymous functions are useful often when you are calling when the argument of a function is another function, and you don't want to give it a name. You just want to stick it in there. But then the third way that you can define a function is what you would use when the function is more complicated, maybe involves some logic. And then you actually write out the word function and then foo of x or whatever it is. Maybe I'll call it foo2. Let's make it different. And then maybe you got something a bit more complicated. Y equals x, just define a new variable, and then maybe w is equal to y, and then okay, at the end of the day you return something which is the output of the function. Let's return w, and this should now be the cubing function. So if let's just test that works. Yes, it works. So that's the third way for defining a function. Okay, so the next thing we need to talk about is we're not really going to introduce you to much in the way of actual programming. We won't need it too much of it, but we will do something that's sort of very basic programming, which is iteration. So I want to talk about a couple of different ways that you can iterate operations in Julia. So the thing we're going to iterate here is the squaring operation, and what we want to do is square the numbers from 1 to 10. So here's the first way you can do it. If you're coming from Python, this is probably pretty close to the code you would write. So first we define ourselves an empty vector. We'll call it squares. Okay, so that's how you define an empty vector. And then we're going to do what's called a for loop. So we're going to say for x in a bunch of values, and what we're going to write in this case is 1:10, which you can think of as essentially something that is representing the integers from 1 to 10. Then you go on a new line, and now I'll indent the next bit of code, but the actual spaces I'm entering here have no syntactic significance. Not like this is not Python where spaces make a difference. And then what I'm going to do now is I'm going to push to the end of this vector called squares, which starts off as empty, the value of x to the power of 2, whatever that is. So that's taking the squares vector and adding to the end of it. And you'll see here this exclamation mark here. That you should regard as part of the variable name, push exclamation mark. The exclamation is part of the name of the function. And it's a convention in Julia to use a question mark at the end of a name when that function is mutating one or more of its arguments. And because we're adding to the end of this squares vector, we are mutating it, we're changing it. We're not copying squares first or something. We're just adding to the end of it. And now, now I'm going to make a new line and say end, which closes the for block. And now if I type out squares, I should see the integers squared from 1 to 10. Okay. The second way we can square numbers to 10, so now here's another way of doing the same thing, is to use what's called comprehension syntax, which is we kind of immediately write down our vector. So I start with a square bracket, and we use comprehension syntax, which is the same idea as the way you often write the definitions of sets in mathematics, if that's something you're familiar with. So here's the syntax. You say, give me the vector of all x to the power of 2, or x being in the numbers from 1 to 10. That's a shorthand version of what we just did before. That's called comprehension. A third method of doing the same thing is to apply what we call the map function, which is a function which takes as one of its arguments another function. So we don't have a name for this function, so we're going to use an anonymous function. We did define squared before, but let's use the anonymous function for practice. So that's the first argument of the map function. And the second argument is the thing you want to apply that function to, in this case, the numbers from 1 to 10. And then we get the same thing we got before. And finally, we have even more terse form of the same thing, essentially, which is to borrow some syntax from MATLAB. So now if I take the numbers from 1 to 10, and I need in this case to put them in brackets to resolve some ambiguity, and if I would just raise this to the power of 2, then that wouldn't make sense because you can't just take vectors and square them. However, if I put this little dot here before the squared symbol, then that's telling us what we want to do is perform this operation element-wise. That is, we want to square each of these elements of this vector. That is, we want to broadcast, the way the language goes like this, we want to broadcast the squaring operation over the elements of this vector. So then that is the shortest way of doing that iteration. Okay. So now that's iteration. Now I'm going to talk a little bit about random numbers. How do we generate random numbers in Julia? We can do this. The simplest random number call is just a call with no arguments, which gives you a single number randomly chosen between 0 and 1 using the uniform distribution. We can already see how we can randomly generate a whole matrix of such things. And if instead of, if I go back here with the up arrow here and edit, and I put an n there, then that will just change the sampling to the standard normal. We will do that in a slightly different way in a minute. If we want to get multiple, suppose we want to have 3 random numbers instead of just 1, and of course we could have just done that, but that's just a special case of really essentially the thing we did above. We can randomly sample from some set, so maybe we have a set of integers, A, B, and C, characters. So there's, sorry, I randomly from a set, a vector of characters, I can randomly sample from that. Maybe I want 10 of those. That's how you do that. And there is also, if you want to do more fancy kind of random things, there's a standard library called random, but I'm not going to demonstrate that now. One thing you need to know is that some statistic functions are not built in, so you have to import the statistics library, for example, to use the mean function. So here's a random number from 1 to 10. Let's get, say, 100 of them. Hopefully that is something close to 5, and it is. So for that mean function to work, we need to import statistics, which will provide some other things. Okay, so that is how far we're going to go for now using the REPL. We're now going to switch gears now and attempt, if we can, to try and interact with Julia in a slightly different way, which is using a notebook. I'm just checking over my questions here. Is the push the same as append? So you use push to, the question is there's a command called a push and there's a command called append. Pushing is for adding a single element, and appending is for adding a vector, basically, is the answer to that question. Okay, so now let's move on. Let's now go find that process that first Julia process that we worked on before. Hopefully it's finished and it's worked. If it didn't work for you, don't panic. You might try following along by continuing to work in the REPL. That's what we call this environment that we've been working in so far, the REPL, spelled R-E-P-L. Actually, I notice you probably can't see the bottom of this because of the banner, so let me just remove the banner for the moment. How do I do that? I've got to hide the banner. Okay, so then, but let me show you how to get these notebooks going. So now what we're going to do is go back to our browser to this page here. that we got to from the resources for the workshop. Now, and what we want to do now is select this second block of code here by clicking on the copy paste icon here. And what this is going to do is it's going to launch a notebook. Now, in the normal workflow, you would launch a Pluto notebook in a slightly different way, but we're doing a sort of a variation on the standard way, which is going to give you customized material for this workshop. So go ahead and copy that there, and then go back to one of your Julia processes. Now, I think we actually have to quit this process and relaunch the process. So I'm going to do that just to make sure that this works as intended. So you may have to do that also. And then go ahead and paste that second code block in and type return a few times to make sure you get the last line of code. If that works for you, it should work relatively quickly. And what it should do is launch a Pluto notebook in a browser. So hopefully that is going to work for most of you. And what you should see is what you're seeing on the screen now. All right. And after a moment or so, you should even see a table of contents. So these are notebooks that are actually specific to this particular workshop. And I'm going to show you one of them now, which is tutorial 1. So go ahead when this appears and click on tutorial 1. And what you'll find there is actually what we've been doing so far at the REPL, stuff about Julia being a calculator, stuff about arrays and so on. And you can see here that notebooks have a different kind of object. They have several advantages. First of all, they're a permanent record of what you're typing, what you're generating. Second of all, you can annotate the code with a bunch of titles and comments and so on, so that it becomes a story that you tell. The third thing about the Pluto note, which is specific to Pluto notebooks, is that they are reactive, and I'm going to explain that very soon. So if we can go back to the table of contents if you want, and you can see all of the material that we're talking about here has a notebook form. But so that you can keep up with us, we're not going to just go through the notebooks. We're going to continue to work one line at a time, and we're going to work in a blank notebook. So how do you get a new blank notebook? Well, you go up to the corner here where it says Pluto, and you click on Pluto. And that will bring you to this page, and then you click on Open a New Notebook. So the second option here, and that should bring up something like this. And go ahead and click in this first kind of yellowish looking box, which is called a cell. We're now ready to use the notebook. Now I can type things. For example, maybe I type x equals 4. And now if I hit return, that's not going to do anything, because it's just going to start a new line without doing anything, because this is a notebook, it's not the REPL. So let's get rid of that return. How do I execute that code? Well, you have a couple of options. The first thing is you can just click on this play button, but that gets pretty old pretty quickly. There's a shortcut for that, and the shortcut is Shift Return. So you're hitting the Shift key and the Return key at the same time. Maybe in case people don't understand my Aussie accent, Shift Return. You're going to do that at the same time, and that is going to evaluate the cell. As I said, you can also just press this play button. Now, if you want to also get a new cell to write in, instead of doing Shift Return, you can do Control Return, and then that will evaluate the cell and create a new one, or you can create a new one just by clicking on these plus symbols. All right. Now, let's do something with that number. Let's compute the square of x and Shift Return to evaluate it. 16, fine. Now, here's something a bit different from, say, Jupyter notebooks, if you're familiar with those. I go back to the first cell, click up there. So now I'm going to click, and I change the value of x to, say, 5, and then Shift Return to evaluate. And I find that the second cell is automatically reevaluated to 25. So the order in which you write things here is the order in which things gets executed is literally the way the things are written. So the order in which you write things, of course, matters. So this is a bit different from Jupyter Notebooks, and this is called reactivity. It has advantages and it has disadvantages. And I'm still learning to live with some of the disadvantages, but it's a very popular and it is sometimes useful. All right, so that's the basics of interaction. One more thing worth mentioning in general, let's go shift return to get a new box, is that you can annotate with text. So the way you do that is, suppose I want to put in some comment here, is maybe I'll give this a name. The way I do that is I actually enter it as code, and I put it as so I enter a string. So this is one way I can do this. I can enter a string, let's say chapter 1, and then shift return, and then I see chapter 1 displayed there, but it's not displayed in a terribly exciting way because I've still got those quotes. So the way I get around that is I edit this and I put MD before that, and that MD stands for Markdown, which is a special kind of string. Maybe you're familiar with Markdown already, in which case you'll immediately want to do something more elaborate. For example, in Markdown, if you put a hash symbol and a space, then that tells us that we want a first order heading. So there you go. If you like Markdown, you'll love Pluto Notebooks. All right. That's a little bit about how these Pluto Notebooks work. Now I'm going to return to our discussion of basic Julia, and we're going to move into a bit of statistics and plotting here. I'm going to talk about things called, we're going to talk about probability distributions. And to do that, we actually need now a third-party package. So that is a package that's not part of your Julia installation, and which leads us to the whole issue of something called package management, which we're not going to try and cover in this workshop. Fortunately, when you're working in a Pluto notebook, the package management is sort of embedded in the notebook, if you like, so you don't have to worry about it too much. So let's load this third-party library called distributions by going using distributions and then going, let's go control return to get it to evaluate that. Distributions not, that's because I didn't know how to spell. Bit of a panic there. Now reevaluating it. And that worked, thank goodness. Okay, so now what we're going to do is we're going to do some random sampling from some distributions. We're going to use, even though we have a built-in function to do it, we're going to use the normal distribution, and we're going to generate some samples. So first, let's fix a number of samples that we're interested in, say 10,000. And now let's not evaluate the cell yet. Let's put in a bunch of lines and see what happens. So we've n equals, say, 1,000. Now let's define some samples. So I'm going to say samples, and I'm going to do some. I'm going to randomly sample from this distribution, from the normal distribution. So the normal distribution, the way you get any distribution using this package is you type the name of the distribution, and then you enter some brackets. Now, if I put no arguments in here, nothing in between the brackets, it says use this default values, which is the standard unit mean and 0 variance. So that's what I'll do by typing normal with brackets like that. Now to randomly sample from it, I just put rand in front, and maybe we want n of those. So that will generate our samples. And if I make one more line, which is now we're going to introduce some nonlinearity to our samples by squaring them. And we're going to use that using that bit of syntactic sugar from MATLAB, where we go dot to the power of 2, which means broadcast the squaring operation over all the samples. And now I'll allow you to actually evaluate the cell. So let's go control return. And you'll see a complaint here. And this complaint is so another idiosyncrasy about Pluto notebooks is that you don't allow you to put multiple lines in one cell, unlike Jupyter notebooks, you have to wrap them in a begin-end block if you want to do that, or split them into separate cells. We'll choose the second option, which is to wrap in a begin-end block. The other idiosyncrasy is that the output of operations in a notebook always appear above the input, which takes some getting used to, but that's the way it is. So we've got ourselves here some samples. We can click on this thing here because we're in a notebook. We have nice sort of display options. We can have a little inspect that in more detail if we want by clicking on the arrow here. Now what we're going to do is fit this sample to a new distribution. So we've squared all the values, so now this is no longer representing normally distributed data anymore, but let's try and fit it to some other kind of distribution. So the way we would do that is we use the fit command. This is a command defined by the distributions package. And let's fit to a gamma distribution. And now I'm not going to put any parameters in here. There's no brackets because I'm trying to learn what parameters I need to use. I just type in samples. Next. And if I execute this, this is going to fit a gamma distribution to my data. So I'll go control return. And now we can see here in the output, we get a specific concrete gamma distribution with various parameters. Now, I want to kind of see how good a job this gamma distribution is at representing that random sample of data. And to do that, we're going to do some plotting in a second. But I can, first of all, just do some more basic things. Of course, I can compute the mean of this particular distribution. I can evaluate the probability density function for this distribution, say at some point, say 1, shift return, and we see, okay, that's the value at that point. It doesn't mean too much to me right now. So maybe what I really want to do is draw a graph. So let's go ahead and do that. For that, I'm going to need another package. But before I do that, I want to show you one. I'll give you a little tip, which is we have this I've said this package distributions is not part of the basic installation. It's a third-party package. How do you find out? How do you get documentation on third-party packages? Well, of course, we can still use the help function, and you see in Pluto when you do that, something appears to the right here automatically. So I could do help on PDF and it tells me about the PDF function. But what if I want to go to the complete documentation for that package? Well, there's a nice package, another package, which is called package online help, which I recently discovered. Let's load that package, control return, and then let's use a tool from that package to go find the documentation for distributions. So what you go now is you type in the @ symbol, you type docs for documentation, and then you type in the name of the package that you want help with, shift return, and that will magically open the repository for that package, and you can then on your browser and you can click on find the documentation, detailed documentation about that package. So now let me just close that window. We finished that little side comment there. Just looking through the questions here, I'm not seeing a lot of questions right now. Maybe things are going too slowly for people. It's only how so fast you can go. I won't assume that. I'll move on and show a little bit of plotting, and then we'll talk about data frames. So let's open a new cell. Control return will do that. And let's import some plotting software. I'm going to import some software. It's called a library. It's called Cairo Makey. Cairo, the city, Makey, M-A-K-I-E. And I'm going to execute a command from Cairo Makey, which sets up the kind of images that it's going to produce so that they will, I will see them nicely in the notebook. So this is an extra sort of annoying step you just have to do. So let's now execute that block. Okay, I forgot to put the begin end block, so let's just wrap that in begin and end. And now that's loaded and set up. So my next block, control return again. I'm going to put a bunch of code. So let me now put in the beginning because I'm going to remember now. And this is going to be, we're going to generate some plots. I'm going to do 2 plots. We want to plot a histogram of the data that we sample. And we want to plot the PDF of our function that we fit and see how they compare. So first, let's define the function. Let's call that function f, the PDF function. So the PDF for what? Well, that distribution that we fit. So that's how we do that. Simple as that. So now we have a simple one variable function to plot. Let's generate some plotting data, some x values. We'll call that xs. And let's plot the numbers from 0 to, say, the number 4, but in steps of 0.1, which I do by putting 0.1 in between 2 colons. So I've got 2 colons, the start value, the step value, and the final value. Okay. Then we want a bunch of corresponding y values. And again, we're going to use this MATLAB syntactic sugar. This says, let's broadcast the operation f over all values of x, s. So that will generate our y values. And now we're going to make a plot. And the plotting command is called lines. That's going to join all those points, those sequences, the points with those x and y values up together with little lines to make something that looks like a curve. X, S, Y, S. It's basically what you would probably guess you need to do. And now I want to overlay on that plot the histogram. And for that, we're going to use the histogram command. But because it's an overlay, I think of this as a mutating operation. And so the command I want to use is the exclamation mark. Otherwise, I just generating a new plot. So let's get a histogram of the samples. And to make sure we're on the same scale, I need to normalize this. So I'm going to choose the normalization option, the PDF. And here we're using, there's an example when we need to use a symbol instead of a string. Number of bins, let's say 40, and we introduce some transparency so we can see the 2 different figures clearly, what that alpha is. And now hopefully that will all work. Then there's one last command which generates the actual plot or forces the actual figure to display, which is a current figure means make the current figure display. So close my end block and shift return, and hopefully, oh, it works. And we see actually that gamma distribution doesn't do too bad a job. So that's plotting. Okay, any questions? Any new questions? I'm not seeing any now. So I'm going to move on to the next thing, which is a brief introduction to data frames. For this, I'm going to ask you to open a new blank notebook so we don't get our variables confused. So you do that by clicking in the left-hand corner Pluto notebook, the Pluto icon. Go down to new notebook, and I need to change look up my new script. Okay, so what I think what we're going to do now is we're going to take a 5-minute break, which you can either use to experiment a little bit and maybe come back with some more questions, and I'll use just to have a little break, and we'll come back in about 5 minutes. I think there's a little... Okay, so that would mean that we're going to resume at 7, let's say 7:20. So let me make a little banner for that. Let's see if I do that, create a banner. Oh, well, that's 7:20 my time. So I don't know what that is in your time.
Yeah, time is not universal.
Okay, so I'll see you in about 5 minutes time from now. There was a banner that says like back in 5 or something, which is not a very useful banner really. So I think we'll just leave it at that and see you in about 5 minutes. Okay, welcome back. I hope you can all hear me. Had a little chance to catch up on some of the questions which were not appearing until I renewed my link. One question which seems worth answering was a question about random numbers. I'm now going to get rid of my picture because it seems to get in the way too much of the time. So let's take that away. So question was about seeding random number generators. So if you want your random number generating to be reproducible, then of course you need some control over that. So you can do this in various ways. There's a in Julia there's a built-in there's a global random number generator which is being used by default, and you can seed that global random number generator by doing the following. I think you would do something like 1, 2, 3, and this would okay, it's going to plain because of that, and this then would seed the global random number generator, but you can also define your own random number generators. So that's sort of the and for example, you can define Mercine twister. Something like this, and give that one a seed. So hopefully that works. And then now, when any random call that you make, if you simply put in the random number generator you want to use to generate the your random numbers, and that will work. That's that question. Okay, now I'm going to turn to data frames for a bit. And now I've opened the wrong thing on my script. Let's go here. I'm only just going to really just do a little bit because of time. Data frames are a huge subject, and you can find workshops, I'm pretty sure, in this conference about using data frames. So the first thing we're going to do is, what a data frame is basically some kind of a table which is in memory. So it's not like a file that's so big that you can't fit into memory. Data frames are about tabular data that you want to manipulate in memory. And here's here's an example of a table that you can construct without actually, not a data frame, it's a table that you can construct using ordinary Julia that we've already learned. And the example I'm going to give here is the way we're going to do it is using a named tuple. So if I have a named tuple and the values are all vectors, then all those vectors have the same length, then we have an example, a simple example of a table. So maybe these are properties of a person or something, a whole bunch of people, their ages, their heights. Let me put in a few numbers here. These are rubbish numbers. Just want to put something in, and maybe whether they're married or not. True. So true and false, you use lowercase letters to define the booleans in Julia. So here is a named tuple. Let's see if that works. Right. So here, I mean, this is essentially all a table is a bunch of vectors with the same lengths, possibly different types, but which have names. That's what a table is, but it doesn't look like a table the way we've presented it. But if you imagine that these vectors here are actually represented vertically, and that you align them all up, concatenate them all together, then it would look like a table, right? So that's a simple table, and it's a very efficient, actually, for many purposes, form of representing tabular data. But it's not very convenient for some purpose. So, for example, if I wanted to just grab a single row of this table, that is the height, age, and status of a single individual, then it's not very convenient using the syntax we've learned to do that. It takes a few steps. It's also quite complicated then to say filter the records or rows of this table according to some criterion. And that's where something like a data frame comes into its own. So let's now load the data frames package. I can never remember, I think it's capital, with using data frames. And now let's create a data frame. And the first data frame that we're going to create, let's call it data frame, lowercase. We're going to create it by just converting the column table that we defined up above. So this is called a column table. And let's do this column table. If we just put that in brackets using this data frame constructor, then magically that's how we can actually construct one of these data frame objects. And the first thing we notice is that it has a much nicer display. So now it actually looks like a table. The second thing that we can do, let's control return to get a new cell, is that we can do what I described before, and we can filter this data frame rows based on some criteria. So we go filter data frame, and then we say do row, and then in this block here we say we specify the criterion. So in this block something has to return either true and false, and in this case we'll do row dot married and say equals true. I don't have to write that, I guess, but and if I do, or let's make it equals false. And if I do that, I get a filtered version of the original data frame based on that criteria, whether someone is married or not. And then, of course, there's a whole lot of other things that you can then do. You can do lots of the kinds of things that, like joins and group by and different kinds of operations that you might know from working on databases in some other context. For our machine learning that we're doing today, we don't have to know much about data frames, but I think you should at least be initiated to them. And as I'm going to explain now, you should understand some basic ways that we access the elements. To do that, I'm going to first, however, show you how you can get a data frame into your computer from the outside world, a data set that from somewhere else. And the somewhere else that we're going to actually do in this case is I'm going to introduce you to something called OpenML. So this I'll just put in the banner. I think I have a banner for this somewhere. No, it's disappeared. So this is just openml.org. And if we go to this website, openml.org, why can't I create a banner? Let's just, maybe we can create a new one. Copy this in there. Copy. And let's view the banner. So if you go to this website, then what you get this OpenML. And what is OpenML? It's a machine learning. It's a platform for sharing machine learning things. So those things could be things like data. You can also share machine learning runs and results and so on. But we're going to just be worried about using it as a source of data. So you click on the left here, you see on the left column on data sets. And if we click here, we see, I don't know where it is. There's something wrong with the site today. It's not coming up on my computer. Come back to that in a moment. Maybe it'll come good in a second. Let's go back to our notebook, which is here. Not sure what's going on there. Maybe that will affect what I try and do here. What I'm going to do now is I'm going to introduce a new package, which is called OpenML. Let's hope that should load. That shouldn't be a problem. And now let's grab a data set from OpenML. Now, each data set in OpenML, as I was hoping to show you here, rather than quite working for some reason, has an associated ID, which I'll show you how to find out in a minute. And we can load data sets in by using their ID. So I'm going to call this data set, what do I call it in my script? I just call it table. So I'm going to say table. I'm going to go OpenML, and we're going to say load, and then we want the data set which has the ID 42638. So that's 42638. Once we've let's just do that and see if it works. It may not work if the site is down. Let's see if it works. At least that worked. That's good. Let's go back to OpenML. It seems to have half worked. Maybe this is something to do with my internet connection. But anyway, on your own, you can go at some point, visit the site, look at data sets, and there's like 4,000 or more data sets. It's just fantastic how many data sets there are. You can search the data sets using various criterion, and then from the ID, you can then load them like we're loading here. Now, after doing this, what I've got here is actually not a data frame, and it's not a column table. It's yet another kind of tabular format called a dictionary column table. And Julia has lots and lots of different tabular formats. And there's some nice software which has been written, which kind of provides a common interface so that you can easily switch between one or other representation. And we're once again going to use this fact by making this into a data frame. So we do the same thing we did before, and we convert this particular kind of table into a data frame by just saying applying data frame to it, the data frame constructor to it, and that should give us a okay, I did that in 2 cells, did I? Okay, so that's 2 cells. So now I've finally got a data frame of the Titanic data set, yay, which we're going to be using in a minute with Samuel. Before I turn over to Samuel, I'll just mention a few ways, more things about data frames. Let's go control return. First thing I'm going to do is introduce you to this command called describe, which gives you a kind of summary of the fields of our data set of our data frame. So on the left here, you see the different variables, which are the different names of the columns. For example, age. And across here, we see various statistics. In particular, you may want to note here that we have some missing values, which we'll have to take care of when we do our machine learning, because our decision tree algorithm may not like the missing values very well. Some algorithms do, actually, but for the sake of illustration, we're going to get rid of those. Right, so that's the describe command. I'm just looking at the time here. I want to make sure I give Samuel plenty of time, and also time for questions. See if I've got any new questions here. I have to just keep renewing this. Okay. Let me show you how to do some basic access here. So the first thing that you want to do is just access a single element of the data frame. So the way we can do that is with square brackets, like it was a matrix. Except what we're free in the second column variable to use the name instead of a number. So I could say, for example, do age, and I can either use string or symbol here. I don't think it matters. That's how we get a single row, a single element. If I want a single row, then I can use one way to do that is to use a wildcard, just like we did for arrays. So I could go colon instead of giving a specific row, and that will give me, sorry, I want to do the column in the other place, don't I? 5, let's get the 5th row and put a colon here, and that'll give us the whole row. Maybe I just give that a name to make it, yeah, that's what that is, it's a row. We can also get columns. The way we get a column is, okay, well, let me just say how we can access an individual element within a row. Let's do that first. So an element within a row, we just use this dot syntax that we saw before. So for example, I could get the age for that row. How do we get a single column? Well, we can access how we get multiple rows. Well, it's more or less the same as we've seen for arrays and vectors. Or did we do that? Maybe we didn't do that. Let me just show you in case we didn't. So if I want to get multiple rows, I could do something like rows 1 through 4, for example. That's how I would do that. I don't know if you can still see this. Let me get rid of my picture here. I'll get rid of the banner now. So make sure you can see the bottom of the screen here. Right, so that's how we would get multiple rows. The next thing is the question, of course, is how do we get a column? I'll show you one way that you can get a column. The single column, one way you can get a single column is just to use the dot syntax that we saw before. Now this is a vector, so I can access it like a vector as well and get a single element in a new way. I think that's all I'm going to say for now about data frames. As I said, it's a huge subject, a huge thing to learn about, and there are other workshops and more details in the tutorial that we provide in the resources. And Samuel may introduce you to some further commands that as needed in the machine learning part. And with that, I'll just check for any last minute questions. There are a lot of questions that aren't ranked very highly, which I tend not to see. Latest. Let's see. Can you close the banner? I can't see what you're typing. Okay. So the data set that we've loaded was this Titanic data set. You can also get information about it using more OpenML commands, but I think I'm not going to go into that detail here. Let's have another last look at OpenML. It's come good. So in OpenML, if we click on datasets, we see them here. And if you click on a particular dataset, it's very slow for me. I'm not sure why. Then in the top left-hand corner there, you'll see the ID of the dataset. Okay, I think with that, I'm going to just go over questions a bit more. Unfortunately, I cannot move the banner. Someone's asked me to do that. I don't know how to do that. Yes, so data frames is very popular in machine learning. There are some other options, but I think for most, unless you have a specific thing like, for example, time series data or something like that, if you're looking at mixed data types, then your the most popular and most mature package would be data frames. Someone's asked how fit calculates the approximation. I don't know. I suspect it's some kind of maximum likelihood thing, but I don't actually know. Someone asked, does ChiroMaker use grammar to make the plots? So ChiroMaker is a relatively new plotting package in Julia, but there's been a lot of development effort going into it, and I think there's another package called Plots, and they're really the two most popular ones: Plots.jl and Makey. The Makey has an extension which is called Algebra of Graphics, which provides a kind of like grammar of graphics. It's similar to that, which is an add-on. So you can, if you like grammar of graphics, you like algebra of graphics, and ChiroMaker has that add-on. And I think that now with that, I'm going to hand over the session, the remainder of my time, to Samuel, who's going to lead you into some actual machine learning. Are you ready, Samuel?
Yep. Can you hear me?
Yes, I can hear you. I'm going to close myself off. We see you. We see you fine, Samuel, but we just see you. We don't see anything else yet.
Can you see my screen now? Anthony, can you see my screen?
Yes, I can see your screen.
Okay, so I'll go ahead then.
Okay.
Hello. So we're going to be going in this last section of the tutorials. We're going to be looking at how we could build a basic machine learning model for the Titanic dataset. And I'm not going to be going through the Titanic dataset, what it is, because Anthony has already gone through that. But I'm just going to show you how the practice on how you could use MLG to build a model for that. So you see already, I've already loaded up the packages we're going to be needing, the MLG and the Dataframes package. So it's something very light and easy. So before we begin, first thing we need to understand about the MLG package is the scientific types, because that's what is at the core of the package. Once you're able to wrap your head around scientific types and what they are, then I think the rest of the package becomes easy to use. So scientific type is that basic stuff you need to know about MLG. So what scientific types in MLG? What do we mean by scientific types? It's actually the way we encode data, or the way MLG models interpret data you passed into it for training or evaluation. So for instance now, in machine learning parlance or in statistical parlance, we know we have different types of data. We have discrete data, we have continuous data, we have categorical, and so on. So in MLG just wants you to think about data in that light, in the statistical light. Are we dealing with discrete data? Are we dealing with continuous data? If it's discrete, is it integers, count data, or is it something that's categorical or something like that? So that's actually what you should be focusing on. MLJ takes care of the rest by allowing you to switch between one data representation to another. So for instance, we know that three, in statistical parlance, we tend to take three as like a count data. So MLD has a way of checking the site type of object. So you could check site type of 3 and you get count. You could check site type of 3.142. Okay, and you get continuous. So that's like expected. Oh, apart from this, you could also check the site type of complicated objects like arrays of these scalar objects. So in general, the site type of arrays of scalar objects should give you an abstract array of the site type of each of those objects. So for example, you could check site type of, let's say I have an array of 2.5 and 8.6. So see, because I have an array of site type objects, objects of floating type, of continuous type objects, basically in statistical balance, we expect, as expected, we had abstract vector continuous. Also, there's what is known as categorical array. That's the way we encode category data in Julia. And MLG has our own way of representing that kind of data. So let me take you to the general structure of scientific types in MLG. So you see here we have missing, textural, ordered factors, multi-class, continuous, and so on and so forth. So for missing, the site type of missing object, any missing object, an instance of, so you get missing. So this is actually very important because this is what we'll be checking in our data, because most data sets are actually messy and missing. So you'll be looking for, oh, do we see missing in the site type information and so on and so forth. So let's check what the site type of the categorical array is. So let me create a categorical array. You don't necessarily need to know how to create this because it automatically converts it for you. So let me just create a dummy categorical array, and let's calculate the size type of this object. Okay. So we see here that the size type of this categorical array is abstract vector of multi-class. Multi-class is one of the ways we encode categorical data in MLG. Another option is if this array was ordered, if this categorical array was ordered, so set ordered equals true. We add another factor. So ordered factor and multi-class are two ways of representing categorical data. Okay, so let's look at how we are going to load the data set in question, because we're trying to build a model for the Titanic data set. So Anthony has gone through a lot of about OpenML. So we're going to use the same OpenML dataset number to load up the Titanic dataset. But this time around, because OpenML doesn't actually generate a data frame, it generates something called a dict column table, which is like a table source, but not necessarily a data frame. So we want to work with data frames here. So I'm going to convert that into a data frame. So that's df. So let me create a data frame called df not data frames. That data frame table. Okay, so last. Okay, so this loads up the data frame. So you can see that I have the Titanic data set. Yeah, I could view just the first element, the first 5 rows of the data frame, standard stuff. Oops. Let me stop. Okay, so I could view the first 5 rows of the data frame. I could also, if I wanted, I could have checked also the last 5 rows of the data frame. So see, I have a view of what the data set looks like. So we can also check the size of the data sets and check how large and how wide data set is. So you see here, its data set has about 891 rows and 8 columns. Okay. Okay. Let me pause for a moment and let's see whether we have any questions of what I've discussed so far.
Samuel,
Yeah.
we're having a bit of static coming in. Do you want to try your different microphone and see if that's any better?
Okay. Is this better now?
Oh, it's just the same. We can still understand you. It's just a little bit annoying, I guess. At least I'm hearing a bit of static. Do you have a different option for a microphone?
No.
Okay, well then we'll just carry on with it. It's just fine. I just thought we would have a try. Okay, carry on.
Okay. All right. Okay. One of the questions is why Scitype of 1, 2, 3 is abstract. Does this have performance hit? I don't think I get this question. Abstract. What do you mean by abstract? Okay. Let's look at another question. Site type doesn't work for me. I get site type not defined. I have data frames. I've loaded MLG and data frames. Are you loading the compiled version? Let's see. Strange. Hang on. So maybe you could open a new Pluto section. Then in the Pluto section, create a new notebook and run using begin end and using MLG, using data frames. This should work for you. Then if you have this, if you make sure you're using using and not import. So if you're using this, you should be able to get Scitype as say autocomplete. So you have Scitype. So I don't know whether that has resolved the problem. I'm confused. The syntax as in OpenML load seems like load was a method of the class object of class OpenML as in Python. But yeah, it's actually OpenML.load, just telling you that the method actually is defined in the OpenML module. That's just what that means. Okay, let's go ahead. Okay, I hope it's not that bad. Is this better now? As for the static?
No, that doesn't make any difference. I think you just carry on the best you can. Yep.
Okay, let's move ahead. I hope you can hear me.
We can hear you. We can hear you.
Can you hear me?
Yes, I can hear you. Can you hear me?
Okay.
We can hear you.
Okay, so let's move ahead. All right, so we could also describe the data set we just loaded. So you could use data frames dot describe. So doing that, you see, you get a summary statistics of each column in the data set, and it gives you statistics that are relevant to the based on the column types. So some column types don't have some statistics. For like P class column, it doesn't have any mean because it doesn't make sense to take mean of categorical objects. So it gives you the minimum and the maximum, stuff like that. So all looks good. So now, after loading data sets and your data frame, you've connected to data frame and you've checked some stuffs. At the end, do we make sure that everything is all good and MLJ is treating our data or is interpreting our data set the right way? So what we could do there is using what is called the schema function. So MLJ provides us with the schema function to inspect our data sets and make sure that all is okay. So we're going to be using the schema function a lot in this tutorial, and it's a recommended function to use in your MLJ workflow. So you have MLJ, so you call schema. So it will call schema on our data frame df nodes. Okay. Okay, so you can call data frame on your schema df nodes, and that gives you a printed pretty table. So you could see each columns in the data set, each column names in the data set, and the corresponding site type of the elements in that column. So for example, now you see that here that the P class column has a site type of multi-class, and the 3 here means that there are actually 3 unique categories, right? 3 unique levels in that P class data set. And something like cabin data set, you see, is a union of missing multi-class 186. So this means that we have about 186 classes in that data set, and we have missing among those data entries. There are missing. Similar to this also, you see a missing here. giving you some flags that, okay, you tend to have some missing data in your, some missing values in your data set. All right. So how then can we handle this? Because I said MLJ treats, expect you to think at the level of scientific types, whether you're dealing with integer data, continuous data, categorical data, stuff like that. So how then do we treat this without having to go down and look at deal with types rather than site types? So what we do is we have MLJ provides you with the coerce function. So the coerce function is what we use to make the column types what we want it to. Basically, that's what it. So you just pass what you want the column types to be, and it does it. So df not. So in this case, you pass the the object. In this case, a data frame, and in this case, I want to change. I want to working with the number of spouses, the number of siblings. That is the sib spouse. Okay, so okay, so the number of siblings slash spouses. So that's what I want to be working on. Okay, so sib spouse. All right. So the number of siblings or spouses is actually something that should be a discrete variable. We cannot have number of siblings or number of spouses of people as 3.2. For example, it doesn't make sense to say, okay, how many siblings do you have? I have 3.2 siblings or something like that. So that variable should actually be treated as discrete variable, whereas it's taken as continuous. So what you do is that you give the name of the variable you want to change, sib spouse, and you pass in what you want to change, type you want to change it to. So I want to change it to count. Count is the way we represent discrete variables. So integers, so when I by count means like integer types 1, 2, 3, and so forth, so on and so forth. So that's that. So I'm going to end. Okay. Oops, double. All right. So you see, this gives me a new data frame from the. So you create each time you create, you pass it. You're doing course. You are creating a new data frame or a new object from the previous object. So then you could now let's check the schema of what we've done to make sure that okay we're on the right path. So you see that the column sib spouse, number of siblings slash number of spouses has actually been changed to something that is discrete, like an integer. That's what we call count. Okay. Now another thing here, another problematic variable here is cabin. So you see here that for cabin we have like 186 classes. That's that'll be too much for an ML algorithm to handle. So it's better to reduce that number of classes into something fewer to make more sense. And you see that also there are missing values in that class data you have. So one option what we could do is to actually split to actually create a new um, column that just has two classes, one with missing, one without missing. So let's create a function that we use to convert that. So let's create a class function. So the idea is I want to convert classes into, I want to convert the cabin class from 186 class instances to just 2 instances through without cabin, depending on whether the entry had a cabin or does not have any cabin recorded. So we have class n. So if is missing n, but it's just something simple, return without cabin. Okay. Else return as cabin. Then you have end. Julia, we have n after the if blocks, unlike Python, different from Python that you don't really need that. So you end the function. So now I have the class function that will help me convert the entries in the cabin column. If the entry has missing, it converts that entry to a string called without cabin. Else, it converts it to something that has cabin. So this is actually converting from multiple classes to just two classes. So let's apply this so-called transform to our data set. So we have the begin. Okay, df. Let's create a new data frame, df2 transform of the original one, data frames dot transform. So data frames dot transform is just basically a way of taking your previous data frame, transforming some of the columns. So you pass a transform, then copy out the remaining columns you have previously into the new data frames. So my data frame is df1. I'm going to copy out, I'm going to transform the column cabin by row, means that for each row in the cabin, so that's by row, for each row in the cabin function, in the cabin column, apply the function class to it. So then the output column will also be named cabin. I know this is quite a lot to get your head wrapped around, but once you get used to it, it's quite intuitive. Okay, so then brackets. Okay, so you can run this. Let's see, we can make it. So yep, this works. We have I see the cabin column has been converted to something strings without cabin or as cabin, right? So like I said, schema is always your friend. Always check schema and make sure that everything you make sure that MLJ is actually interpreting the data the way you want it to. So call schema on the data frame 2. Let's see what's going on. Yeah, so you notice that cabin is now textural, right? Rather than multi-class or other factor, which is like categorical. So we actually want a categorical or multi-class data, multi-class site type, rather than textural. So what we do is that, like I said, MLJ provides you with the coerce function. So you could just coerce the previous data frame. So I'm going to coerce that CE. Okay. So the cabin column, I want it to be multi-class. Multi-class. Okay. So see here now. Let's check the site type to make sure it's actually did what we wanted to. So checking schema, you see, yep, we have what we want. We have converted it from something that was previously 186 classes with missing class to something that's just 2 class with no missing. So you see that's okay. Yeah. So before we continue, because there's still some missing elements here to take care of, let me pause and see whether we have any questions. Okay, yeah, it's a question here. Is changing the site type from discrete to continuous important for machine learning or conceptual detail? So it's more of conceptual stuff, and that's actually what you could work without that. But MLJ model is actually built on the idea that based on the idea of site types. So it allows us to suggest to you models that will probably work well on your data sets. So you could actually search for models that will do well on your data set or work on your data set. So that's one of the reasons why thinking that in terms of scientific types is actually better than machine types. Another question is, Julia has several deep learning packages. Why should I choose MLJ and not one of the others? So MLJ is actually more aims to be like more general purpose, not just for deep learning. Works on classic machine learning models and as well as deep learning also, because we have an interface to Flux and stuff like that. So it's aims to provide more like a general purpose like interface to all those different frameworks. So rather than having to learn one interface from one package or then learn how to use another interface from another package and stuff like that, you have everything in one place. So you just have to learn one interface, and it works well with other packages, including Flux, because I think we have an interface to Flux, MLG Flux, right? Then prior to MLG, what we had in the ecosystem was we had scattered packages. So with decision-tree.jl was this individual package, different other packages. So if a user wanted to apply any of those models, he had to learn the package syntax for each of those, low-level syntax for each of those packages. And if he wants to switch to another model, he has to learn the package syntax for that new model. So MLG kind of provides like a general interface to all those models. Yeah, describe the new show or print. Describe is more like giving you some statistics on data. Show and print are more like just giving you representations of like the data frame, like giving you for print maybe like textual representation of the data frame, stuff like that. Describe is more like statistics on summary statistics on each of the columns of the data frames. All right, let's move ahead. Yeah, it was a cool question. What are the advantages of MLJ compared to Python's scikit-learn? Composability, that's one of the key goals of MLJ. You could compose models in ways that you probably have never thought of doing. So Python has some limitations in that regard, or at least if you can do that, it's actually very, very difficult to compose models in Python. So we compare composing models in MLG, the number of lines of code you type is small compared to if you could do the same thing in Python. And there's some cases where it's very difficult to do it in Python's scaling. Okay, let's move ahead. All right, so before I treat the how to handle the embarked column, let's just personal preference. Let's split the data. Let's show how you could split your data set into a training and a test data set. So let's do that. So MLJ has what they call partition. So it allows you to split. So basically you can think of it as a way of splitting your data set into training and test stuff. But it's more complicated than that. You can do some other quite fun stuff. So df. So I'm going to create two new variables. df means the training data set, df test, the test data set. So I call the partition function on that and pass in the updated data frame, which is df3, and I give it the training fraction. So I want 70% training data set. That's what 0.7 means. So split such that you have 70% of training, 7% of your data set used for training. So Then they can also pass a random number, a number used in random number to sample or to see that your random number generator. All right, so we run this. Obviously, we have two data frames. First data frame, the training data frame. The second data frame, the test, which is the test data frame. Okay, so then we could check the number of rows. So let's go data frames. N row df. So you see here we have 624 rows. Let's make sure that data did what we want. So frames dot n row df test. Sorry, df3. So that's, see, it's roughly 70% of the data that's provided. All right. Okay. So now let's look at how we could handle another way of handling the missing data. Previously, we just converted it because we had a lot of classes and there was just some missing values in that class. So yeah, so we have a lot of classes and then there was missing values in that class. So now we want to look at another way of handling missing data, rather than just binarize and giving you two variables, two classes. So MLJ provides what we have, what is known as transformers, or what people regard as unsupervised models. So we're going to use a transformer, show how we can use a transformer to actually fill out the missing values in the embarked data set. So we want to fill that out. So if you look at the embarked data set, the description of the original, the describe function here, embarked, you see that it just has two missings, right? Not quite much compared to the number of rows in that data set too. So it's good if I just use some kind of imputation method. Okay. So let's build a unsupervised model or transformer to do that. So I'm going to name our transformer cleaner. Cleans out the missing data sets. So I'm going to use here what is known as a fill imputer. Okay. So this is just one of the several transformers MLJ provides. We have feature selector, we have standardizer. For example, you want to standardize your data sets, you could use a standardizer. So we have pretty much most stuff, transforms you need for data analysis inbuilt as models. Okay, so that's how you create a model. So you see that this model has some parameters, features, continuous fill, finite fill. So continuous fill, finite fill, and count fill are just functions that actually handles each of those columns. So continuous fill, we handle continuous columns in a data set. Count fill, we handle count columns. That's columns that has the count site type. While finite fill handles columns that have like either ordered factor or multi-class site type in the data. Features there is just a way of restricting your model to just work on a subset of the data set, like in terms of columns you want to handle. So in this case, we really want to focus on embarked. So I could just limit it to say, okay, just do this cleaning on the embarked column. Don't bother about other columns, right? So, oops, features. All right, so you see that's updated that. So let's move ahead. So that's a model. What I want to point out or to stress out here is that there's another models in MLJ is not, they don't, you can't train on a model like you do in scikit-learn. So in scikit-learn, you build your model, you have methods that are kind of like on those models. So you could call fit on those models, you could call predict on those models. So in MLJ we separate that stuff. So that's another very key a key difference between MLJ and scikit-learn. So we separate the idea of a model from the idea of training a model. So to train a model, we use what they could known as machines. So in MLJ we have models and we have machines. Models are like the data that goes into the machine. So imagine like you have the computer system and you give it data, and the machine is like a robot and just the training and spits out data, stuff like that. So machine is what actually does the training. Model is the specification of how the machine should go ahead doing the training in the internals and stuff like that. So you can think of it like that. So in order to train this model, I will create a machine. Okay, so machine. So let's call my machine match she. So we have machine. So to create a machine for unsupervised model, you pass in the model, the instance of the model, which is cleaner in this case. Then you pass in a data frame, right? Because unsupervised models don't need a target generally though. So you pass in the data frame, in this case DF, our training data frame, which used to do the stuff. So for this, we actually create a machine for you, so a machine, right? It's not done any training, just creates it. We've not instructed it to do any training or stuff like that. We could train this machine by calling fit with a bang, meaning that this machine is this. I think one thing that might be confusing here is you might think that machine is actually mutating your model. So don't be deceived. The machine is not actually mutating your model. What it's actually doing is storing some of the fit parameters in the machine. So the machine is like an object. So it's as you train it, it's recording information of the training process and stuff like that in itself. So that's what we have the bang here. It's not mutating anything about the model. All right. So you call mash. So it fits that trained good. So we could also check, let's see what happened to this machine, what's the parameters. So just like in scikit-learn, we can also check the parameters that the machine fitted based on the model input. So let's check that. So fitted params is the function you call. You call fitted parameters and you pass in the machine that has been trained. So it will tell you the information of the fit parameters, like what parameters are needed to have been fit. That's the hyperparameters that was fit during the models. Sorry, not hyperparameters though. The parameters that was fit during the model. So match she pass that, and voila, you have see here features that was seen during the fit. You have the univariate transformer, count field, median, and stuff like that. So you see, this is actually what was modified, the embarked columns. So it filled it with S. Anywhere you saw missing, it's filled with S. So this what's important there. All right. So now we have trained our transformer to do the fitting, to do the transforming. That means anywhere it sees missing, it transforms the data and gets rid of missing. So let's actually get rid of missing both the training and data sets. So to do that, we have the transform. So when you train a transformer, you can call transform on a given object, input data frame or table, and it transforms it based on the specific details of the transformer. So let's transform our machine. So mlj.transform machine df, right? And this actually transforms your test data set, right? There's no more missings here, and you could check that schema BFC. There's no missing. So likewise, you could also transform your training data sets. No, that's your training data set that was transformed. So you can transform your test data sets. mlg.transform machine give test. Okay. So that actually transforms your test data set also. And you can also check the schema of that. Okay. Good. So let me pause it again, see whether there are any questions we need to address. Yeah. Someone's asking about stratified partitions, and I think Anthony has addressed that already. We have ways of doing that using cross-fold validation. I think we have a stratified cross-fold validation you could use for that.
Yeah, you can also just do a stratified partition directly.
Oh, yeah.
Yeah.
Okay. And what else? I think the rest has been answered. I think good. Let me refresh to see whether there's any question we missed. Okay, no new questions. I take it that we're understanding stuff. Okay, that's good. Let's move ahead. All right. So now we've transformed our training data sets to DFC and our test data set to DFC test. So now let's unpack, because we want to build a supervised model now. So let's unpack. A supervised model has targets and features. So we want to unpack each of these, or what you call split. Split the targets from the features. So that's what. So for the training data set, we'll split the targets from the features, and for the test data set, we'll split the targets from the features. So let's do that. So we're going to be using what is called unpack. So it provides the unpack function for this. So it's also another nice function. Simple way you can think about it is just a way of splitting the target from the features, but you could do much more than that. So if you check the doc string for unpacked, you could do more than basic stuff. So for now, we're just going to deal with the basic stuff. So y is the target. So the way the function works is the first output, it turns a tuple. The first output is the target, while the rest is the features. So when you remove the target, the meaning obvious is the features. Unpack, so it passes in the data frame you want it to unpack the target from, and you tell it which column is the target. So in this case, the survived column is what we are trying to build our model. We want to know, build a model to predict whether an individual will survive or not. On on that. And the other one is features. Okay. So let's check the Scitype of this object in terms of MLJ. But Scitype is what we do. So Scitype of Y, it's actually a vector of multi-class. So it means that the target is actually categorical. It has levels, right? And that's just 2 levels in it. That's good. We could check what are the levels. Right, 0 and 1, so just 2 levels. That's good. So you also want to check, maybe you want to check the Scitype of X. It's actually a table. for X, it's better to check the schema. Okay, so you notice here that the survived column is no longer here, right? Have I transformed impact? Oops, I'm using the wrong df. I should have used dfc. Tell me what I noticed that. So this should be dfc, not df. So I said schema is your friend. So using schema, you pick up this kind of silly mistakes. DFC is our transformed data set that have removed this missing. So we can see embarked is not having any missing value. Okay. All right. All is good. Okay. Likewise, we can do the same thing for the test data sets. So let's transform it. So Y test and X test. Same way you use the unpack functionality. So unpack EF test, okay, double equals to survived. So like I said earlier on, what this will do is take your data frame, which is DF test, and tell it which column is the target. That's what is specified, telling us the target is survived. So it's to split that to Y test, and the remaining one will be your features, which is X test. So we run this. Again, you have to a tuple. First the target, the other one is the table. So you could also check earlier on, like we did, you could also check the Scitype of Y test and the schema, okay, of X test. All is good. Oops, I get X test. Why are you making that mistake? So DFC test. Okay. Schema is your friend. All right. So now let's go into model building. We've converted and we split our data sets into training and test, and also we know the targets from it. So we have training target, test target, um, training features, test features. So having this kind of data set, we might be overwhelmed. What kind of models can we apply to this kind of data set? So luckily for us, MLG has a model search and matching functionality. So we could actually filter out models that actually work well on a data set. So the way you do it is called models matching. You pass in your X, which is your features. So you're going to find models that match your features and your target. And Y it runs, so it gives you, so here we have about 4 models. See the names there. We can actually pass this to Dataframe. Should be possible. It's yep, it's possible. So this is a better view. All right. Most things in MLG is actually table sources, so you can always convert them to maybe more appropriate table if you wish to. So you see that we have 4 models: constant classifier, decision tree classifier, deterministic constant classifier, random forest classifier. So for this model, for this tutorial, we're going to be using the decision tree classifier. All right. And we can check more information about about each of these classifiers. So maybe we want to say, oh, maybe after scrolling through the stuff, you needed more information about each of these classifiers. You could then do doc. So you could check the doc string of each of these stuff. So I give you the name of the classifier, decision tree classifier, and I also give you the package because there might be different packages that have that. But this decision tree classifier, it's the one from BetaML package that actually fits your data set. Other decision tree classifiers might not be perfect for your data set, but this tells you that the decision tree classifier coming from the BetaML packages will work for you without any issues. BetaML. So let's get the basic information. So for now, this is really basic, but there's actually projects that we're currently undergoing to make this actually more pretty and more informative. So look out for that. So then after we've checked the what the model is all about. I said, oh yeah, seems this is what I want. This is what I need. Thank you, MLJ. So then you then have to load the data. So what do? You begin and so let's call it tree. So you load the instance of the model. You have to load the model, I mean. So you load the instance of the model, the type of the model first, then you instantiate that. So to do that, we have the @load macro. So @load macro takes in the package name, right? So as a package name, the model name, so decision tree classifier. Okay, and also you need to add the package it's coming from. So most times, yeah, you might not need to add the package name if maybe that's the only model in the entire MLJ universe. So, but for decision tree classifier, that's not the only model. There are several other models that has that same name. So you also need to add the package name, right? So you add the package name, beta ML. Okay. So after you brought it into your environment, then you then create an instance. So first, I imported the type. I brought in the type, so we have that model type. You could name it anything. I just named it tree. You can name it anything. Then after that, I then instantiated it. So we have like an object. So I created the model. So this is like the type. This is actually the model, right? An instance of the model. So we can see that the model has several hyperparameters that we're not going to actually go into because we don't have time for that. All right. So yeah. So now we have our model. What next? What should we do? Earlier on, I said model. Creating a model is not, you can't train using your model. Model is just giving you the information. You have to create a machine to do the training. So when you pass a model to the machine knows, okay, how to go about the training stuff, right? So machine is like a robot that just takes input from model input and does the training and gives you output and can do several other stuff. So I need to create a machine if I actually want to train this model. So I use begin. So let me call it match T this time around. Get machine. So earlier on, for unsupervised model, we just add the model name and we add the features, right? But for supervised model, apart from the features, you also need to have the target, right? So you have Y target here, passed it to it. Okay, then let's run this first and see that I created a machine, nothing happens, just a machine. So you want the machine then to fit the stuff, you can now call fit match T, and it gives you your fitted stuff, right? So we have a trained machine now, right? Machine trained and stuff like that. Okay. So what do you want to get predictions? Okay, we trained this machine. Someone just comes around and says, okay, look at this group of people. Let's see, will they survive on the Titanic or will they die? So you say, okay, cool. You have the predict function similar to scikit-learn, but so you pass in your machine. So earlier on in unsupervised models, we use transform. Transform, you pass in your machine and you pass in the feature, what you want to transform. So for supervised, you pass in your machine called predict on it, and you pass in the the test data sets. So all right. So match T. Okay, so you see that you have different predictions here. And this is actually what we call probabilistic predictions. So each row of the prediction is actually a probabilistic object. So when you see in MLJ, you see univariate finite object, it tells you that this is actually a probabilistic prediction. So it might be strange to people that maybe you call predict in scikit-learn and you get like actual predictions in terms of whether or not someone survived. This gives the probabilities of each case. So probability. So if you look at, for example, the third item, the probability of 0 is not survived, 1 is survived. So probability of not surviving is about 0.2 for, and the probability of surviving is about 0.8 for that third individual, right? So this probability distribution, so probability predictions. So what if you want to get you want actually that you want individual predictions like singular predictions whether or not someone survived. So there's another option what you could do. You could just say, okay, let's call predict mode. So MLG provides the predict mode function. You pass the machine, right, and you get X test. We just come around and see you get actual prediction. Survived, not survived, like that. Okay, another way of doing it is that if you have your probabilistic predictions, you could call mode, you could broadcast mode on each of those stuffs. It will take the most likely. So this actually predict mode is giving you the most likely case. So predict that and similar answers, you get the same thing. Survive, not survive, so on. Okay. So what if we want to, after we've done all these predictions and we're confident that we've built a great model and stuff like that, how do we know we have built a great model? So you might want to actually test the performance of a model. So for this, we have what is known as performance metrics, performance measures in MLG. So MLG has a vast array of performance measures. So in case you're looking for performance measures, maybe you want to use some in your package, you could just check out MLG base for that. So let's check out some performance measures. So I have a list of all the performance measures MLG has. You could just call them measures with open bracket. So this will give me something 50. So I'm going to pass it to a data frame. I'm going to create a data frame on it. So we see we have a lot of measures, bias loss, bias scores, and stuff like that. So for probabilistic predictions, let's get we might want to use a log loss, right? So let's call log loss as the probability. Our predictions predictions are always the first argument, while the actual is the second argument. So you write test, okay, and you see this gives you the log loss. Also, you could also check. Let's see. Maybe you want to check accuracy. Accuracy doesn't work for probabilistic distributions. You need actual scalar, like in terms of levels. You predict categorical. So categorical predictions, whether or not someone survived or didn't survive. So for that case, maybe I have a capacity to get the mode of it. So this gives me, like I said earlier on, this gives me scalar predictions, like the way we have it in scikit-learn. So then pass the white test, so it gives you accuracy measure. So the other one was log loss, and this was accuracy. Okay. So I think with that, we've come to the end of the tutorial. So I'd like to let's check if there are any questions. Can MLG find a PyTorch model for your given dataset? No. We have Flux. We have links to Flux, what's known as MLG-flux.jl. So you can check out MLG-flux.jl. So Julia, we use Flux.jl. So that's our deep learning library. So yep, we have an interface to that library. Okay, I think other ones has been answered.
Perhaps I'll answer the question, which was also, I think, implicit in the previous one. How would you do a neural network, and why does models matching not find any? Well, the reason here is that our data set at the moment our features have mixed type. So we've got features like cabin, for example, which is categorical, and then we have continuous features like age, I suppose. So most models, raw models, don't handle data of mixed type. So we don't find many when we provide data of mixed type. If you were to provide some kind of pre-processing to your data, for example, one-hot encoding, which would convert all your categoricals to continuous, then all your features would be continuous. And when you went models matching X, Y, you would find a lot more models, including the flux models, which are the neural network models that we interface. So that's that question. Any more questions? Last chance for questions.
Yeah,
maybe
we give a lot of time for questions. We wanted to get your
question.
questions.
There's another question. What is the log loss? So log loss is also known as cross entropy. So maybe you know what is that. So if it's a classification problem like this one, what you would do is you would look at so the model in that case is predicting, our model is predicting probabilities. So you would go to each particular observation and you say, well, was the true value survived? Was the true value predicted or not? I'm sorry, you take what the, what would you do? You take the, examples where, now I'm going to mess up the definition, trying to do it off the top of my head. Why don't we just leave it as, it's another name for it is the cross entropy, and you can look up the definition so I don't eat my word, put my foot in my mouth. Any other questions? Oh, there's two more questions.
There was one on ROC curve.
And how would you plot the ROC curve? So there, would you like me to answer those?
Yeah, you can go ahead.
Yeah.
Go
So there's a function to compute the points on an ROC curve. It's just called ROC. And if you type $ROC, you can get hopefully get some information about that. There are also tutorials that can demonstrate that. Perhaps I'll mention, share my screen for a moment.
Okay.
Is that right, Samuel?
Yeah, so you can go ahead.
If you go to MLJ, I don't know, if you search for mlj.jl, hopefully that's the best way. That's one way to find it. And you can find, well, okay, it's taking me here. So I click on documentation, and this is the basic manual for the package. You can find a lot more here. And in particular, beginners will be interested in this section called Learn. So if you click on Learn, there's a bunch of resources. If you actually are an experienced machine learning practitioner already, I highly recommend this tutorial called MLJ for Data Scientists. So if you already know about machine learning and you're simply wanting to transition from another platform, for example, that's a really good tutorial. And there's an example of an ROC curve in there. Other basic things that you would do, confusion matrix, and then of course hyperparameter optimization, controlling iteration, and so on, and pipelining models. So when you take several models, so for example a supervised learning model and some pre-processing steps, and you combine them together into one super model. So this particular tutorial lives at a site called Data Science Tutorials, which have more tutorials on how to use MLJ, including some basic things, but also some less basic things, and some versions of a popular textbook called Introduction to Statistical Learning. So that popular textbook has a bunch of laboratories. I think they're written in R, and they've been converted here to Julia, so that might be something interesting to you, and also a bunch of end-to-end examples. So there's a link to this tutorial site from the Learn thing here. Okay, let's see if there's some more questions. Of Bayesian models. So at the moment, we have only kind of a proof of concept for some probabilistic programming packages. There's a probabilistic programming package in Julia called SOSS, S-O-S-S, and we interface just some simple models for there, but not really full integration at the moment. Let's see what other questions we have. When I go to something, I see this package was updated 1 year ago. Oh, that's because you're not actually looking at ML. So there's a question about a particular site. So you've looked for MLJ and you've been taken to a site, but that's actually a site that just summarizes other sites. So it's not, you're not looking at the raw, the actual package, or the information about when it was last updated is out of date. So if we go to MLJ is being actively developed. So if you come here, I mean, you can see 7 days ago there was something. So this is actually just a kind of a package that sucks in other packages. Yeah, the main one where all the activity is called MLJ base, actually. What other questions do we have? Why not do data preparation, including imputation, and then split into test and training?
That's possible.
You can do that.
That's possible, yeah. It's your preference.
Yeah. It kind of depends. If you are using an imputation method which generalizes to new data, you may want to include that as part of your overall pipeline.
Exactly.
But then if you're using a method that doesn't generalize to new data, then you have no choice and you have to do it first. What is the practical purpose use of separating the model and the machine like this? Well, the actual reason that we do this has to do with model composition. So when we designed MLJ, we had the idea that we wanted to more flexibly be able to combine models. So, for example, a popular way of combining models in machine learning competitions is called model stacking. And so there in model stacking, you blend the predictions of multiple models together and so on. And if you try and build such a stack using, say, another package like scikit-learn, you just can't do it. You need a third-party package. So when we designed MLJ, we wanted model composition to work very well. And it just turned out that this machine, this extra little abstraction of machine, was very useful for from the model composition point of view. So it seems just a little bit weird if you're not used to it when you're just doing ordinary fit predict. But when you go ahead, when you generalize this and you're doing model composition, combining models, then the same syntax can just be used that you're already used to in that more advanced setting. So that's the reason for it. Any other questions? Two more. Oh, does MLJ interact with fastai.jl in any way? No, it doesn't.
No, not at the moment.
No, and are they distinct from one another? Well, there's actually a Julia discourse. This question was asked on Julia discourse, but I'm not sure everyone has access to that. But if you look on Julia discourse, you might see something like comparison between MLJ and Flux, that kind of discussion. But I'll answer here. So Fast AI is extra boiler, sits on top of Flux, which is a kind of a core package for providing neural network or deep learning type models. So if you're focused on deep learning models, then Fast AI provides you with a lot of extra sort of boilerplate code that you would want that sits on top of that. So it makes it convenient to actually more convenient to quickly build and train models using neural networks. So MLJ is a machine learning toolbox, but it's not focused on neural networks. So it's more general. It's interested in giving you a possibility of interacting with a much larger class of models. So in that sense, their focus is different. At least that's my best understanding of the differences of the packages. So if all you ever want to do is neural networks, you might find that Fast AI is more helpful to you. But if you're interested in comparing neural networks with some other models, then maybe you want to use MLJ. So that's kind of an answer. Is it one machine per transformer? For example, can you have one machine that imputes and the decision tree? So each machine points to a single set model or set of hyperparameters, but it's possible to have different So, I mean, I'm not quite sure if I'm answering the question.
I think in terms of pipeline, you could combine transformers, you could compose transformers if you wish to, then you pass them into a single machine. That's possible.
Yeah, one design pattern that comes up here is quite interesting is target transformations, because in a pipeline, when you want to transform the target, first you transform the target and then you use that in your training. But then after you predict, you want to inverse transform your target back to the original scale that you were interested in. So that means you have to use the learn parameters twice. Once when you transform for the sake of training, and once when you inverse transform so that you return the predictions back to the scale that you started with. That means you're using the same machine, but different operations on it, or if you like, the same learn parameters, but you use them twice. And this machine sort of abstraction actually makes that much easier. So when you can have when you're combining models like that way, you can do that. You can reuse the same learn parameters at different places in your pipeline, essentially. Hopefully that gives sort of an answer to that question. And there's another question.
Yeah.
So this is
I think it's talking about reinforcement learning models.
Reinforcement learning. No. So I think reinforcement learning is going to remain out of scope for MLJ, at least for the moment. Yeah. Any more questions?
Seems there are no more questions.
Seems like there's no more questions. Well, thank you everyone for joining us. I hope you got something out of this. And it's preparing a workshop that works for a wide audience is quite challenging, but I hope we've managed to you've each managed to get something out of it. Thanks for we got some positive feedback. Thank you very much. Okay. Have a good, enjoy the rest of the conference, and perhaps we'll see you around in one of the shared forums. I'm going to now end the broadcast.
Yeah.
Cheerio.
Bye.